Okay, in this next section on logic, we're going to be covering a couple of specific types of compound statements. So the first thing I want to talk about are the tautologies and the contradictions, and then we'll move on to equivalences and negations. So, statement that is always true no matter what the input values of the atomic statements is called a tautology. And this is the basis for the majority of mathematical proof techniques, which we'll talk about in a little bit in this section. It's not covered in the textbook, but it's something we should definitely talk about for context. So a statement that is always false, this is called a contradiction. And the majority of statements majority of compound statements we work with, at least in the context of logic, are going to be a contingency. So these guys are sometimes true, sometimes false. Let's do an example. So construct a truth table for this compound statement, this compound proposition. So the first thing we need to sort of map out is the size of the truth table, both in number of rows and number of columns. So we have two atomic statements. We have a P and a Q. So we have 4 rows to our truth table. And we have, let's see, 1, 2, 3, 4. We have 4 logical connectives. 1 unary operation, we have the negation, and 3 binary operations. So we have 4 logical connectives, so we're going to have 4 columns to our truth table. Remember, I'm doing truth tables a bit more linearly than the textbook. I'm working left to right, not in the structure of how the compound statement is given. So the first thing I'm doing is the truth values for the negation. Then I'm going to move on to this disjunction in the parentheses. So that's second column. Then I'm going to move on to this conjunction. That's the third column. And then finally, outside of the brackets, I'm going to move on to the conditional. So actually, let me get rid of this. Yeah. So doing 1, and then 2, and then 3, and then, oop, that's not a 4, and then 4. And remember, except for the negation, which is the only unary operation that we're covering, the rest of the logical connectives are binary, meaning regardless of how many columns you have currently in your truth table, you're only ever working with 2. So just pay attention to choosing the right 2 columns to combine into one or into the next column. So here are our values of P. So not P is going to reverse all of these truth values. So instead of true, true, false, false, we should get false, false, true, true. So the way I have it color-coded is the logical connective highlighted in red will affect the columns that are highlighted in red. Next, we have the disjunction. So P or Q. So again, these 2 columns are being connected with the disjunction, and the only way a disjunction is false is if both the atomic statements are false. Next, we're moving on to the conjunction. So it's the not P and the P or Q. So take these 2 columns and combine them with a conjunction or combine them with an and. And remember, the only way a conjunction is true is if both truth values are true. Otherwise, it is false. And then finally, the conditional. We have the not P and P or Q comes first, and the Q comes second. So basically false implies true. And by our definition of the conditional, that equals true. We could go down the rest in the same fashion. So our result here is all four of the truth values are true. So regardless of what happens here, so these are our inputs, P and Q, our atomic statements. No matter what's going on with the P or the Q, no matter what P and Q represent, they're always giving us a true statement. And this is what we mean by a tautology. This is a tautology, a compound statement that is always true. So here's another example, not a truth table, but something similar. So the question is this a tautology, yes or no? Or is it a tautology, a self-contradiction, or neither? So a bit more specific than just a yes, no. Well, these outer brackets here are sort of grouping all of this together. So this disjunction is combining two things, this conditional statement and this rather large compound statement. Now, the key here is P implies P is always true. There's only two options. If P is true, then true implies true equals true by our definition. And if P is false, false implies false is also true by our definition of the conditional. So basically what we have here is a statement that looks like this. This is always true. P implies P is true, so we have true or something. And according to our definition of the disjunction, one true makes a true. So true or anything equals true. So yes, this, regardless of what P, Q, R, S, and T represent, this big compound statement up here is a tautology. This is always true. Now this is not the type of statement you would want to analyze using a truth table, because we have, let's see, P, Q, R, S, T. We have 5 atomic statements. So the number of rows would be 2 to the 5th power. 2 times 2 times 2 times 2 times 2, which would be 32 rows. And then we would have an individual column for each logical connective. So we would have well over 100 operations within the truth table. Not something we would want to take the time to do. So within the topic of tautologies, self-contradictions, I think and contingencies, the most important one here is the tautology. I mean, this forms, exactly what I have here. This forms the basis of mathematical proofs. This is not something you'll see in this section in the textbook, but I think it's important to talk about this now to give context to what we're doing and why we're doing it. Okay, so consider this. The product of an even number and an odd number will be an even number. So basically, even times odd equals even. Now in the first chapter, we talked about inductive arguments and deductive arguments. Now we could frame an argument using either type of logic. But recall, only deductive arguments could be used to prove a statement. So this statement here, the product of an even and an odd number will be even. That may seem obvious, or after a couple of examples, you may be convinced, but our goal is to prove that this statement is always true for all whole numbers, or all integers. Okay, so like I said, let's do an inductive argument first and see what that would at least look like. So remember, inductive arguments are basically proof by example, which is not a legitimate proof technique. But here I give you an even times an odd, and we get an even. And again, an even times an odd, the result is even. Could do it a third time. Even times an odd, our result is even. We could keep going forever. Technically, even times odd is again even. So it looks like this is a property that should always be true, but this is an inductive argument. Proof by example. What does this prove? Well, this proves nothing. All we've done is, for these 4 specific examples, we've proved that this property holds, but there are infinitely many other numbers that we haven't verified this property for. So we want to show that the product of an even number and an odd number will be even. And we want to show that this is always true for all infinitely many integer values. So now, alternatively, we could take a deductive argument. So let's see, an even number can be written as 2 times p for some integer p. So basically, even numbers are multiples of 2. Hence, they can be expressed in the form 2p or 2x or 2m, whatever symbol or variable or letter you want to use is fine. So here's our even number, here's our odd number, and so let's see if I can, oh yeah, I could switch up the black pen. So even times odd should look like this. 2p is the even, 2q plus 1 is the odd number. And p and q can be any whole number or any integer value from negative infinity up to infinity. So this is a general statement about all integers. So if we, let's see, if we distribute the 2p times 2q, and then 2p times 1, we'll have 4pq from the first product and a 2p from the second product. All right, so now this is looking like it should be an even number. Remember, definition of an even number is any multiple of 2. Okay, so we can factor out a 2 from both terms, and now we have 2 times this 2pq plus p. Now we could have factored out a p as well, but that doesn't help us here. What we want is a multiple of 2. So 2 times a number, this is going to be a number. Not sure what it is, but it's definitely going to be a whole number. If you take a whole number, multiply it by another whole number, you still have a whole number, double it, you still have a whole number, add another whole number to that. So we're still dealing with a whole number here. So this product, which we started with, even times odd, gave us 2 times something, multiple of 2. So this, when I say it down here, it is an even number. This is the it, the product of an even and an odd. So what we've done is taken a deductive approach to show that an even number times an odd number will always be even, and we've shown that this holds true for all integer values. This type of argument is a very common proof technique, and this is called conditional syllogism. And we could generalize this to any number of implications or conditional statements, but if P implies Q and Q implies R, well, according to conditional syllogism, then P should imply R. So we basically have this train of conditional statement. Oh, that's not a Q. P implies Q, Q implies R, so P implies R. Each step in that previous proof was a conditional statement. Now we can verify that this is a legitimate proof technique by setting up a truth table for this compound statement. So we'll need, let's see, we'll need one column here, we'll need one column here, then we'll need to put them together with a conjunction, then we'll need this conditional logical connective, and then finally the outer conditional. And we have our definition of the conditional statement, and that's pretty much all. Well, we have definition of the conditional and definition of the conjunction. Those are the only two pieces of information we need to construct this truth table. And notice that there's 8 rows because we have 3 atomic statements, P, Q, and R. So the number of rows should be 2 to the 3rd power since we have 3 statements. Okay, I'm just going to go in and fill in the truth table. It might not be a bad idea to pause the video with the blank truth table just to make sure you're constructing the truth tables in the correct manner. But what's important here is this statement, regardless of what P, Q, and R represent, is always true. This is a valid proof technique. So if we got into the next couple of sections, we would formally define the ideas of valid and invalid. But here, I just want to give some context to why we're talking about tautologies and truth tables. Okay. The next topic I want to talk about is logical equivalence and De Morgan's laws. So, the word equivalent is defined in different ways in different areas of mathematics. In the context of Boolean logic, we will say 2 propositional formulas. These are compound statements. So 2 propositional formulas are equivalent, logically equivalent, if they have the same truth values regardless of the truth values of their atomic statements. Or another way of looking at this is 2 compound propositions are equivalent if and only if the bijection between them is a tautology. But I think for our purposes, it makes sense to focus on this first definition. So these 2 definitions are pretty much equivalent, but the first one will make more sense because we're using truth tables anyway to explore what's happening with these compound statements. Okay, so here's 2 compound statements. P implies Q, and not P implies not Q. I used both the symbols here. I used both the symbols for negation. They're both very common. The tilde means negation, or this sideways L means negation. So if you see that, I think our textbook uses the tilde for negation. But if you see this symbol, it means the same thing. Interchangeable. So now my question is, what are the truth values for these 2 compound statements? The first one should be relatively easy because it's just the conditional statement, and according to the definition of the conditional statement, This is true, false, true, true. Only false when the antecedent is true and the consequent is false. And if we analyze the truth values for this second statement, not Q implies not P. So for this first row, we would have a false implies false. So not Q is false, not P is false, and false implies false equals true. Down here, if Q is false, then not Q would be true. And if P is true, not P would be false. And according to the definition of this operation, conditional, true implies false equals false. So that's right here. And if you complete the truth table, you'll see that these two compound statements, these two compound propositions have the same truth values. So for similar inputs, you get similar outputs. So we say these two statements up here are logically equivalent, meaning they work the same way. On this previous slide, this statement here, not Q implies not P, this has a special name and particular importance. This is called the contrapositive of a conditional statement. So the contrapositive of if P then Q would be if not Q then not P. Now going back to the idea of mathematical proof, where this idea of logical equivalence comes up is that if you want to prove a mathematical statement that looks like this, it is okay to just prove a statement that is equivalent to the statement you want to prove. So if you want to prove something, you can work with if you want to prove a conditional statement, you can work with the contrapositive of that conditional statement. And many times this is easier than the conditional syllogism, which is like a direct proof technique. Working with the contrapositive allows us to work with counterexamples. So to show a statement is false, we just need to show it's false for one example. And that's one example, one case where we use the contrapositive. We'll come back to this later, like I say down here. But first, we're starting with a conditional statement, and then there are a few related statements based on the conditional statement that's initially given. Contrapositive is one of them. Okay. So back to the idea of logical equivalence. So here's two compound statements, two compound propositions, and let's construct a truth table for both of them. So the first one, not, parentheses, P and Q. So let's see, the P is true and Q is true, so the P and Q would be true, but there's a not in front, so we basically have not true, which would be false. And if P is true, then not P would be false, or if Q is true, then not Q would be false. False or false equals false. And we could go through again. We could go through the truth table and complete the next three rows, and we will see that these two statements have identical truth values, which means they work the same based on similar inputs, which means they are logically equivalent. These two statements in particular represent half of a very important logical property. It's we call this De Morgan's law, and it's not a property specific to mathematical logic. This is a property that applies in many other places. So what we just showed last slide, let me just bounce back for a second. Between these two statements, what do we have here? So this first statement, we have the negation of a conjunction. Okay, negation of a conjunction. And the second one, we have the disjunction of two negations. And down here we show that these two compound statements are equivalent. So we could say that the negation of a conjunction is equivalent to the disjunction of the negations. It might be less complicated to think about it symbolically, but this represents half of what we call De Morgan's law. Well, one way to think about these is the distributive law for the negation. So this negation affects the P, it affects the logical connective, and it affects the Q. So basically we have not P, not conjunction, so that's disjunction, and not Q. Oop, didn't mean to do that. Okay, so De Morgan's laws are helpful in analyzing the string of conditional statements in a direct proof or using a conditional syllogism argument, among other places. So far, let me go back a slide. De Morgan's law is the only time we've seen the negation of a compound statement so far. But there's other logical connectives besides the and the or. So when we're negating compound statements, let's say we want to negate a conditional statement, we haven't defined how that works yet. We've defined the conditional, but we haven't defined the negation of the conditional. But we have another statement that's equivalent to the conditional statement. And this other statement is a disjunction. And we know how to negate a disjunction. That's 2 slides back. That's right here. So it's not going away. Well, this number 2, this is the negation of a disjunction. So we know how this works. Now, if we want to negate a conditional statement, we can take another statement that is equivalent to the conditional and replace the conditional. So we could replace that P implies Q with a not P or Q. And so that brings us over here. Now we can negate this disjunction. And that's according to De Morgan's law. So basically distribute the negation. So we'll have a not P. So the 2 nots, like 2 negative signs, cancel out, and that's P. Then we have the not or, which gives us the and. And then we have the not Q, which is here at the end, not Q. So the negation, so we basically substitute in an equivalent statement for the conditional because we don't have a rule to distribute the negation on the conditional. But to negate this conditional statement, our final result is this conjunctive statement, P and not Q. Okay, so let's give it a little bit of context. Rather than just working with P's and Q's, let's work with an actual conditional statement. So in this example, let's give the negation of the statement, if you build it, they will come. So this is an if-then statement. We don't explicitly have the word then, but it's implied within the statement. So this is equivalent to saying, if you build it, then they will come. Now, we want to negate this statement, and to do that, we can reword the conditional to look like this. So we know that these two are equivalent, so we could replace one with the other. If you build it, then they will come. So here's our first atomic statement. You build it, that's our P. And they will come, that's our second atomic statement, that's our Q. So this conditional statement is equivalent to not P or Q. So when we go to negate the conditional statement, the negation of if you build it, they will come, intuitively, it might make sense that it should be something like, if you don't build it, then they won't come, or if you build it, they won't come, something like this. But it turns out that negation of a conditional statement is a conjunction. So we've replaced our conditional with this disjunctive statement, this statement using the word or. So now we have to negate the not P or Q. And we saw earlier that this is P and not Q. So let me just, right here. You build it and they don't come. So let me switch over here. So you build it. That's the P. Conjunction, that's the and. And not Q. Negation of Q, they don't come. Okay, so the negation of if you build it, they will come is you build it and they don't come. This is similar to the rationale behind the definition of the conditional statement that I gave in the previous set of notes. Okay, and then finally, and just real quickly, the converse, inverse, and contrapositive. So basically, you first have a conditional statement. Once you have a conditional statement, then you could talk about the converse of that conditional statement, which basically means change the order. So instead of P implies Q, it would be Q implies P. You could also talk about the inverse. And the inverse is the negation of all atomic statements. So the inverse of P implies Q would be not P implies not Q. And then finally, we could talk about, and this is the one we've talked about previously in this set of notes, the contrapositive. And that's basically combining the operations of the converse and the inverse. So we change the order and negate both statements. On the next slide, I have them all defined nicely. So we're starting with a conditional statement, if P then Q, and then we have these three related statements, converse, inverse, contrapositive. Converse changes the order, inverse negates the statements, the individual atomic statements, and the contrapositive does both, changes the order and negates the atomic statements. We've already showed earlier that a conditional statement is equivalent to its contrapositive. And if we construct a truth table for both the converse and the inverse, so here's conditional, here's converse, here's inverse, and here's contrapositive. If we construct a truth table for each of these four, well, conditional we already have, contrapositive we've already done, we will see that conditional is equivalent to the contrapositive, and the converse is equivalent to the inverse. So a conditional statement is not equivalent to its converse, and the conditional statement is not equivalent to its inverse. Okay, so that about does it for this set of notes. As always, if there's any questions, please send them my way.